right, folks, it's Bass Action, back in action here. On this page of notes, I'm going to introduce a new function called the greatest integer function, and then I'm also going to review graphing piecewise functions with you. You'll notice that I already have some t-charts drawn in here. This will just make the video go a little bit quicker for us. You're welcome to pause the video and write down those t-charts if you want, but it allows me to just kind of walk through those and talk through what's going to happen there a little quicker. So let's take a look at our integer function. I will note that on mine, I had to fill in this little notation of these brackets on 3a and 4b. Yours probably already shows that, but just in case for some reason it didn't print on your side, go ahead and fill those in. So an integer function is kind of like what it's going to sound like. The greatest integer function is that all of our y values are going to be integers. So it's going to take whatever number we put in and it's going to basically chop off the decimal is kind of the easiest way to think about this. So when you either see just the int notation or you see these brackets around the x, those both mean the same thing. So when we take a look at our t-chart and we want to evaluate this, what we're thinking is that, for example, if x is 0.5, so I put a 0.5 into my integer function here, no matter which notation I would use, then what it's going to do is it's going to chop off anything to the right of the decimal, and it's going to say that my y value is 0. So, of course, if I start at 0, it's going to be 0, and if I pick 0.5, it's going to give me a y value of 0. But when I get to the integer of 1, it's then going to chop off any decimal to the right, and it's going to tell me that my function evaluates to a 1. So that means what's going to happen here is on this first part, I have a nice little segment here, and when I get to 1, I'm going to give myself an open circle, and now my graph has jumped up a step. Then at 1.5, it's also going to evaluate to a 1, but when I get to 2, it's going to jump up to a 2. So again, I'm going to have this nice little flat step there and an open circle, and it's going to jump up again. I could continue following this pattern, and this will go over, and I'll get an open circle at 3. This function is going to be odd. I can rotate this around, and I can write these steps backwards. I could certainly evaluate my t-chart backwards if I wanted to, but I do generally think that it's easier to go to the right and then just reflect everything on down, rotate it down. So the domain of the function that we're working with, what we can find is that any x value is acceptable. So our domain is negative infinity to positive infinity. Our range, however, we're going to write this in our set notation, and we're going to say our y such that y is any integer. Remember, an integer is any whole number, positive and negative. So this is often referred to as a step function, and you heard me say that word as I was describing those little pieces. Those are each considered steps. So let's take what we know about transformations that we did in the first video and apply that to the integer function. And again, I gave you a t-chart, but I'm going to walk it through first in terms of a physical transformation. So on the first one that I have here, I have the integer function and I have x over 3. And what we want to think about, remember this is a transformation on the x, so it is going to be a little bit more complicated. What we're thinking is that this is moving at 1/3 speed. So remember, think of this as your grandma is driving, and grandma's driving at 1/3 speed, which means it's going to take her 3 times as long to complete the journey. So in our case, what that means is each of our steps are going to be 3 times as long. So that's how I can do that in terms of just utilizing a transformation. Now the height between the steps is still the same. So I can back this up and do it in the opposite direction. And that's how we can do this graph just using transformations without the t-chart. Now, if I do it with the t-chart, what I'm going to be noticing here is that at 1, when I put 1 into the function, I get a 1/3. Well, that 1/3 is going to evaluate the integer function to be 0. And if I put a 2 in there, 2/3 is still less than 1, so it evaluates to 0. But 3/3 evaluates to exactly 1, so it hopped up when it got to 3. 4/3 is 1 and 1/3, so that's still not yet to 2, so that stays at a 1. And 5/3 is going to be 1 and 2/3, also still not up to the 2, so it evaluates at a 1. So that's another way to look at how to understand why those steps are staying the lengths that they are. On the next one, our transformation is going to be on the y. We can see here that what this is saying is that the distance between our steps is going to be 3, okay? So if we want to, kind of accidentally got a few little things on my graph there, sorry. So if we want to graph it just using transformations and not thinking about the t-chart, I'm going to think the length of my step is still just 1, so the width of this step is still the same. But then I'm going to jump all the way up to a 3 to make the next step. And I'm going to jump all the way up to a 6 to make the next step. And again, then I could go backwards and reflect this down. Now, when we look in terms of the t-chart, we can think, why is that happening? I put in some numbers there. So at 0.5, we know the integer function is going to evaluate this 0.5 to become a 0, and 3 times 0 is, of course, 0. So that kept it at the bottom. When I put a 1 into the integer function, that, of course, returned a 1. 3 times 1 is going to give me a 3. So I should find the 0.13 on my graph, and now we can see that great big step. At 1.5, if we evaluate that again, the 1.5 is going to evaluate to a 1, and that, of course, still keeps it there at a 3. At 2, it's going to jump up, and we get 3 times 2 is going to give us a 6. So that helps us understand a little bit better why those steps are as far apart as they are if you do forget how to do it with just transformations. Now let's take a look at a piecewise function. A piecewise function is exactly what it sounds like. We're going to take pieces of different functions and put them together, and it has to remain a function. What I've done here for you is I've given you a t-chart that I would create if I were going to graph this first piece in my function, this square root. Now, what we do know on this square root function from our first video is that this is going to have a horizontal shift and it's going to have a horizontal reflection. So not only is my square root function, instead of pointing in this direction to the right, we know it's going to point to the left, and it's a 5 that's going to make that radicand 0, so it's actually going to shift to the right and then point to the left. And if we set up our t-chart, we will get those ordered pairs. So one technique for doing a piecewise function is to actually graph the entire function first. So I'm going to actually go ahead and plot all of these points that I've graphed here. So I'm going to plot the point 5, 0, and I'm going to plot the point 4, 1, and I'm going to plot the point 1, 2, and I'm going to plot the point -4. Oh, I meant to write a 3 there. You might have already noticed it when you were looking at that t-chart, wondering what was wrong with that. Let me go ahead and fix that. I don't know why that's not erasing for me, but I'll just mark it out. There we go. Now it is. It's catching up to me. Okay, so this would be if we were going to graph the entire piecewise, the entire square root function. But the piecewise function that we're working with tells us that we only want the places where the x values are less than 1. So if I come over here to the x values of less than 1, this is the only part of the piecewise graph that I want to keep. So what I can actually do, and what you can do on your paper, is just physically erase anything that isn't in that domain. So we keep all the pieces that are inside the domain that we wanted, and then we could be done with that. The only other thing we would want to change on this is that our piece says that this point right here is supposed to be an open circle. So what we can do is erase that and make that a nice open circle for us. Again, iPad's not erasing it particularly well for me right now, so I'm not totally sure why that's doing that, but oh, there we go. Now I got it working. There we go. So now, our last piece that we can do is going to be the graph of this line. And again, I'm just going to show you how we can do it if we wanted to graph the whole thing. So I would graph my y-intercept of a 3, and then my slope is a -2, so I'm going to go down 2, and I'm going to go over 1. I'm going to go down 2 and over 1, and down 2 and over 1. So when I graph in this line, if I graph in the whole line, you probably have a straight edge there. I'm working on the iPad, so it does make it a little bit funkier. That would give me the whole line. Now remember, our entire final graph has to pass the vertical line test, and this doesn't yet. So what we're going to do is we're going to look at what portion do we want. Well, we want to keep the portion of the graph that's between the x value of a 1 and the x value of a 4. So I have a whole bunch of this that I'm actually going to erase. So I'm going to put some points on the spots that I want to keep. So I want to go from there up to actually where I have my nice open circle there, and I'm going to erase everything else. So if you're working on yours, again, you can just erase, just physically start erasing your paper there. So we just erase all these parts that are outside the domain that we don't actually want. I always like to check the endpoints last, and this one says that at x equals 1, we do in fact want a nice solid circle there. So at x equals 1, it should be at the point 1, 1. That's not inside my little circle there. So our graph is going to finally look like that. So that's what our piecewise graph would look like when we're all finished.